Hello friends of the Ladybug. This is video number 10 of my Ultimate Ladybug course. If you haven't watched my previous videos, please go back into the playlist and rewatch so you know where we came from and where we go to. Nevertheless, you can watch this video as a standalone tutorial if you have some prior knowledge in importing weather data into Ladybug. In this today's tutorial, we will jump into the fascinating world of solar panel adjustment with Grasshopper, Ladybug, and Galapagos. So are you ready to unlock the secrets of maximizing your solar panel efficiency? It sounds extremely boring. Imagine this. The sun is moving. We're talking about a fixed solar panel. Fixed. It doesn't move with the sun. The sun is moving. And over the year, also the sun angle changes. So finding the sweet spot of the panel is actually not that simple. I was actually looking for a good example to use Galapagos in a very simple way, and this is the best example, really. And why is it so crucial? Well, the angle of the solar panel determines on how efficient your solar panel works. And to get it right will create more renewable energy. That means you need less energy from non-renewable sources, and that's good for the environment, etc., etc. Okay, let's jump in. All right, you can see here, I tested already a bit. This video was actually not that simple. But very quickly to recap, super quick, fast recap. This is our project. It's in Rwanda. What we did in the first videos, we brought in weather data. We modified the weather data because the original one is quite far. It's like 60 kilometers off, and it's a different altitude. So we tried to modify the weather data together with some components from Dragonfly. You don't need to do that. You can just use any weather data and just play with that. So you could have just import the weather data, and then we have our weather data panel. The Ladybug import e plus weather data panel, and from there you can just go. This is the same output as with our modified weather data. It's not the same numbers, but it's the same principle. So you don't need all this stuff. You only need the weather data to follow along with this exercise. The tool we're using, and I'll just show you this here. Okay, is the Ladybug directional solar irradiance tool. So what does this do? It's a tool to compute the hourly solar irradiance or illuminance falling on an unobstructed surface that faces any direction. The calculation method of this component is faster than running Ladybug incident radiation studies on an hour-by-hour basis, and it's slightly more realistic since it accounts for ground reflection. However, this comes at a cost of not being able to account for any obstructions that block the sun. It has some drawbacks, so it's not accounting any object within your property, but I think it's a very good tool nonetheless. It doesn't automatically solve the right angle. It's just measuring the angle. That's all it does. So we talk about the automatization later on. So what do we need first here as an input? We need the location. By the way, I'm using here, I'm using an alternative, more extreme location here. It's from Sweden, just for test purposes. Pushing this away. This was my original test. Looks more complicated than it is really. I will build it nicer. So I'm using a weather data from Oslo, so where we have a more steeper sun angle, because in Rwanda it's pretty much at the equator. So it's pretty clear on how the orientation of the solar panel must be or should be. But we can test anyway. So with using this Oslo weather data. What else do we need? We need the direct the direct normal radiation and the diffuse horizontal radiation. That's what we need. And then we already have an output. So we can add a panel here. In the report there's nothing, but the total irradiance it's actually not the total, it's a total per hour. So it calculates the direct and the diffuse and the reflective light, or the reflection. So if there's ground reflection, we also can specify that. In our case, because it's going to be farmland, we can choose here 0.2. That is our ground reference. Hoppla. Here it says 0.2 would be grass. I think we can use that. We can change, of course. And then we have another input here is the anisotropic and isotropic. I think if it's false, then it's the isotropic sky. And you can read, or I can read it here, so you know what is it all about, and we can test what works. A Boolean value that sets whether an anisotropic sky is used as opposed to an isotropic sky. An isotropic sky assumes an even distribution of diffuse irradiance across the sky, while an anisotropic sky places more diffuse irradiance near the solar disk. The default is false, so that means the isotropic sky is used in that case, and we can check if there's any difference. The anisotropic will have more emphasis on the sun location. Now the values, what we get here, we can use one of the most important tools in Ladybug is the deconstruct data tool. That's just the most important, really. I use it in every script, or pretty much every Ladybug script I need to use this, or Honeybee or Dragonfly. And how that works, we just place it in here, we get the values. We get the values separate from the header. And then we can just create an average. That should give us a very good understanding of the output. So this is the average per hour, what we get for the whole year. Now, the problem is we don't see anything. I mean, we don't see anything in the model except for this previous example, which we can turn off. So we just have a point here. And we use this point as the placement of our visual representation of that panel, of that solar panel orientation. So we build everything in Grasshopper in this case. So we can go here in vector. We use the XY plane, and I will explain why. I just want to make sure that I really capture the right orientation here, because it's a bit, yeah. So with this one, this is my plane. It's not yet referenced anywhere, so I need to use a point. This is my location, and that I can place in here, and then I have my plane. Now the default orientation, because we have already an orientation here. The default orientation, the surface azimuth, this is the rotation parallel to the ground, north, south, east, west. And the altitude is basically the slope, or the angle, the altitude of the sunlight. So in order to get that right, it says here north is 0 or 360, and then we have east is 90, south is 180, and west is 270. So that's one condition. And then the other one is the altitude, or the slope, is between minus 90 and 90, where the 0 means it's facing south, facing the horizon south. That's the default value. Because the default for the azimuth is the south direction. So it's facing south, and it's vertical, basically. It's the standing surface. At the moment, we don't have that. So how to prepare really for this? So first of all, we rotate first our thing so it fits the condition, and then we rotate it again. It's a bit yeah. So first of all, we need to rotate this. Rotate. We can rotate the axis. This is not good. Rotate in 3D. That's what we're gonna use. So we take our plane, and then we rotate it. And by the way, here I need to always make sure that this is not radians. I need to change this to degree. Very important, degree. We also need to make sure that our center point is placed. So this is our center point. That the point in the middle is our center point of the rotation as well. And then we can use this here. I'm turning off the original plane, so we only see the new plane. And here now, the problem here is it rotates in the opposite direction, right? So as you can see here, now north this is still correct. Then I rotate. Here it says 90 is east, and south is 180. As you can see, that's the problem. This is the first problem. This is north, but then it rotates against the clock, and that's the first problem. So we need to kind of add something here. So now it's basically, it moves, it's the correct condition. And we also need to make sure that we have here 360. So now it rotates in the right direction. So this is one thing. And then the other thing is the slope. We need another rotate object. We can place this. This we already solved it. We can use this slider later. Hold on. It's not that it's a bit, it's actually more tricky. Because although we solved this rotation here, the surface altitude is a slightly different problem. So we'll solve that actually first. We can go in here, and because at the moment what it does, it's lying on the ground. So if we add another rotate object here, and we can disregard that for a bit, we don't use that. So center of rotation, that's clear, and the angle is different. So in order to get to the default situation, we actually need to rotate this so that the Y is facing upwards and the X is facing to the south. So we can do that by adding a slider. If we place this here, that doesn't work. So it rotates around the Z axis. So we need to specify the axis it's rotating around, which is the X axis. Oh, sorry, X. The X vector. That's what we're gonna use. So if we go to 90, this is our default orientation. As you can read here, a value of 0 means surface is facing the horizon, and the value of 90 means the surface is facing straight up. But the default is 90. The default is 0. As you can see here, in order to make that rule happen, we need to make sure that 0 is upwards. So 0 is vertical, and 90 is facing upwards. So in order to do that, we just create this condition here. So this is our default, and we assume that this is now the 0 rotation. I hope I make it clear. So, and I know there are other planes. We could use a vertical plane, but this is not the same. I'm very cautious about this. So we can add here just a number. This is our starting rotation, which we assume is 0, although we rotated it by 90 degrees. And we can hide that. So this we're not gonna touch anymore. And now we make the rotation for the altitude happening. So bear with me. This is a bit complicated, I know, and maybe there's another way, probably more elegant way. I like to do things step by step, and then maybe afterwards I find that actually I could have done it a bit different. But that's how I do it now. So I use now the default orientation. Now my center point is still the same. And here I also take the degrees. So we have the degrees. So now this is the rotation I'm starting to work with. And now I can add a slider where I say for the altitude is 90 and minus 90. And again, I need to add the X unit here. So it basically does this. And here's the same problem. I need to make sure that it rotates in the correct direction. This is also super important. So 90 means it's lying down, 0 it's facing south, and minus 90 means it's facing downward. So I changed again how the orientation works with, or the rotation works. I think it's a bit, maybe I'm overthinking it a bit, but I just want to be very clear with how we orient it first, and then we continue. So we have this, we have our rotation that is not linked yet. And then because this now is a bit sidetracked, we need to actually bring this back. So the rotation on the Z-axis is important here. So we actually want to rotate this object around the Z-axis also. So this goes here, the origin is still the same, and now we have the ability to rotate. Opala, we want to show this one. Now we can rotate in the Z-axis in the right direction, 360 degrees, and also in that direction. So now we are in the correct. Now it looks correct to me. And maybe now I'm completely wrong, but that's how I would start. And now we have the 360. This is the azimuth that goes here, and we have the altitude, which goes in here. now we can look at the output. And here, I mean, now it doesn't change not much because it's facing upwards all the time. Yeah, and here exactly there's a mistake now. I'm making a mistake. Why is that? Let me check. Yes, actually that was already correct. Sorry. So I don't need this. I don't need this. Is already the right. It's already the right rotation for the altitude. So the altitude, I don't need the -1 rotation option. So we can play with this. I know that because I'm using the weather data from Norway, from Oslo. That means in the south, I would need to get, so the panel needs to be orientated to the south in order to get more. That's why I know that I don't need this multiplication by -1. So I don't need to reverse the angle, because now I can see that if I play with these values here and this, then I can kind of trying to optimize. I think this is like 130. That I know that this was the value, one of the values I got before with this weather data. That means this is the average output, or the average watt per square meter for each hour. And if you place it, if you orientate your solar panel slightly wrong, then you easily end up with only half the amount, Anyway, so we can play around with the sliders, but what if we just want to automate that? And this is the best example for Galapagos. Although you can, of course, play with the sliders yourself, it's much more fun to use Galapagos, and it's a super simple example to show how it works. All right, let's go here. Math, object, sets, curve, surface. Where is it? Here. Galapagos is the evolutionary solver. I'm not sure if you ever worked with it, but yeah, just very quickly explain how it works. We need to provide a fitness. The fitness is what we are aiming for, and it always aims towards the maximum or the minimum, depending on how you set up your script. But looking for the maximum is here the best option. We want to maximize the efficiency of our solar panel. Actually, it goes to reverse, so it's not like you take something and place it here. You go out from Galapagos into a tool. In that case, is the fitness we want to test. How fit is it? And then we can use the genome. This is we place into the sliders. We have two sliders which determine the effective orientation, and I can just, with shift, I can place the second one. So now I have two sliders hooked up. Now we can go in here, and we have two different solvers. They work slightly different. I will not go into depth, but you will see the magic happen very quickly. So let's use the simulate annealing solver. You can start here, and you will see how that all moves around. It's pretty cool. Start. Let me do this again. I want to see this thing moving around. Okay, start. Here you have an option to see the thing moving. So in a way, what it does is just tests more and more different angles and records the best fitness, the best combination of the two. And you see that on the top, you see that which one was this was the best tested. Well, it keeps testing. Also, the movement becomes narrower and more narrow. But I think you get the point. So it just tests, and always basically places the highest on top. I will just stop here, and you can then go here and reinstate selected genome in Grasshopper. I think that's it. That's the last one anyway, or you can go back. Yeah, but this was the best result, and it's probably super accurate. Well, we could now test if there's any difference. Oh, okay, it's just to close this here. If I change here this to float point number, I'm curious if that gives us a bit more accuracy. I mean, it won't change much, I guess, but let's try. Same here. Let's do this. It's pretty much the same, so I will just stop this here. We have 113.6 0.5, which was pretty much similar as before. Just stop it here, and it just goes back to this, to the best result. And there's another, so this now would be my, this would be the best orientation for my solar panel if I would be in Oslo. And now I'm changing this here. I also want to show you the evolutionary solver, which works slightly different. Let's start here. It takes a bit longer. This works slightly different. It already does something. It's already trying to find, interestingly, it already found the best value, it seems. Let's see if it can, if it can grade it even more accurate, can be even more optimized. Let's see. I think it's pretty much the same. We can stop this here. You can see it's pretty much the same orientation. Now I very quickly want to test this on the Rwanda weather data. Well, yes, let's do that, and then we can test something else. I'll just stop that. Put this here. We put this location. We use the direct normal radiation and the diffuse horizontal radiation. But yeah, so we have this, and in the same position, it gives us a slightly different picture. So let's see what happens if we run this. As I said, it's gonna be facing upwards because of the equator. But yeah, I think we can stop this here. It's pretty straight upwards. Yeah, it's not 100% straight up, straight, which gives me hope. So it's facing slightly north, which makes sense because it's just slightly below the equator to the north, to the south. So yeah, it's just, yeah, it really makes sense. Yeah, I hope you like this video. Subscribe, maybe become a member to help me to create even more and better videos. And yeah, keep in touch, text me, comment if you have a better solution. I'm always up. I'm also learning myself. There's no end to learning. And it's the best thing to do. So see you. Oh yes, in the next video. We will move forward. Sorry, I only covered one tool in this video, but I thought it really deserves its own video. The directional solar irradiance tool, and even better with Galapagos, of course. So yeah, see you in the next video. Ciao.